Welcome! In this multivariate calculus tutorial, we're going to go through some problems in grad, div, and curl. And so if you're interested in that, then stay tuned. So let's begin here with a little summary. Let uppercase F or bold uppercase F be PQR, and let this be a vector field on 3 space. And so you can think of a vector field as a force field, or metaphorically like current in a river. So at a point x, y, z, it has a magnitude and a direction like a river does. So at a given point in a river, the current will be pushing something in some particular direction with some particular strength of the force field. Okay, so nabla, this is this triangle here. This is a differential operator containing differential operators in each of the components with respect to x, with respect to y, with respect to z. Grad f is this differential operator operating on a scalar function lowercase f, and when that happens, we get a vector containing partial derivatives in it. The first component is the partial derivative of f with respect to x. The second is f with respect to y. And the third is the partial derivative of f with respect to z. So div f can be thought of in aid to memory as the dot product of this nabla with the vector field uppercase F. And so if you were to take that dot product, you would get the sum of each of these 3 functions differentiated partially with respect to each of the letters x, y, and z. So the sum of those. So px plus p plus qy plus rz. Okay, finally, curl of the vector field uppercase F can be thought of in aid to memory as a cross product of this nabla with the vector field uppercase F. But you don't want to, I think, from my experience, you don't want to have to calculate this cross product every time you calculate curl. So this formula here can make that a bit easier to do in practice. Okay, and so if you like acronyms, then we can also do this another way. So if instead of PQR, I use ABC and I write curl of uppercase A, uppercase B, uppercase C, and instead of XYZ, I use lowercase a, lowercase b, and lowercase c, then this line right here can be remembered perhaps more easily as uppercase C, uppercase B, uppercase B, differentiated respectively with respect to B, C, and A. Okay, subtract. Now we write these letters the other way, B, C, and A, differentiated with respect to lowercase c, lowercase a, and lowercase b. So that's if you like acronyms. You know, if you have to remember this in order to be fast on an exam, for example, but you don't have a formula sheet, well, this would be a good way to do that. All right, so next point, if the work done in moving the object from the point A to the point B is independent of the paths taken, then we say that the vector field F is conservative. If F is a vector field, that is the gradient of some function, scalar function, lowercase f. In other words, given the vector field uppercase F, there exists a scalar function lowercase f such that the vector field is grad of the scalar function, then F is conservative. Okay, F is called irrotational if the curl of F is the 0 vector everywhere for all points x, y, z, and F is called incompressible if div of the vector field F is 0 everywhere. So this is scalar 0. This up here is vector 0. Okay, so we have a few theorems. If the scalar function F has continuous second partial derivatives, then curl of grad F is the 0 vector. If vector field F defined on 3 space has continuous partial derivatives and the curl of F, that should be a bold F, is the 0 vector, then F is conservative. The converse is true defined on some domain U. Okay, so I think there's a little bit more to that converse. If F has continuous second partial derivatives, then div of curl of the vector field F is the 0 scalar. All right, so the following exercises, which we're going to do together, are found in the book by Stewart. So let's get started on those. Okay, question 1. Now, I'm going to write these vectors vertically, but it's easier to type them horizontally. All right, so we have f is x y squared z squared, then x squared y z squared, then x squared y squared z. Okay, and so this here is our A, this here is our B, this here is our C. All right, and so then curl of f, let's use this formula right here. So C, and I guess I should continue to write this vertically. So CA B minus BCA. But now let's put the subscripts in. So rather than use lowercase ABC here, I'm just going to translate back to XYZ. And so B plays the role of Y, A plays the role of Z. Oh, hang on, C plays the role of Z. Okay, and A the role of X. All right, now over here will be Z, X, and Y. Okay, so simplifying this, we'll take this third entry here, and I'll continue to use the subscript just because it's easy. Then the first one is our uppercase A, and then we have uppercase B. Okay, so here we have this. Now simplifying this, we need to take partial derivatives. So differentiating this function with respect to y partially, we have 2x squared y z. Differentiating this with respect to z partially gives 2x y squared z. Differentiating this partially with respect to x gives 2x y z squared. Okay, doing the same over here. We have 2x squared y z, then we have 2x y squared z, and then we have 2x y z squared. Okay, and now subtracting, these two are the same, so we have 0, these two are the same, so we have 0 there, and these two are the same, so we have 0 there. Now this is the 0 vector, so what we see then is that curl of f is the 0 vector. Okay, so this was relatively easy. Let's do this a second way, just so you can see what I'd rather not do in general. So curl of f is given by del cross f. So we put the vector I hat there, j hat, and k hat. Then we put the components of the del operator, and then we put our a, b, c, or just f written horizontally there. And so that's x y squared z squared, x squared y z squared, x squared y squared z. Okay, now let's take this cross product, which is just innate to memory because these are vectors there. So we have this determinant, and so you can see that there's just a lot of rewriting of things that take time to rewrite. And then crossing out the row and the column that the I is in, this is what we have there. And then that is next to I hat, and then minus determinant times j hat, and then we will have plus a determinant times k hat. Okay, so what goes in here is what happens when we cross out the row and the column that the j hat is in. Okay, now coming to the coefficient of k hat, we cross out the row and the column that the k hat is in and write down what remains. Okay, and now we take each of these 2 by 2 determinants, and so that is the derivative with respect to y partially of x squared y squared z minus the derivative with respect to z partially of x squared y z squared. So that is that one. And then all of this is times I hat. I hat, remember, is just a placeholder. And then minus in brackets times j hat. And then we're going to get plus something in brackets times k hat. Okay, so what do we have here? We have the partial derivative with respect to x of x squared y squared z. Subtract partial derivative with respect to z. Hang on. Shouldn't this have been? No, that's fine. Okay. X, y squared, z squared. And then over here we have the partial derivative with respect to x of x squared, y, z squared. Subtract the partial derivative with respect to y of x, y squared, z squared. Okay, so simplifying this, we now differentiate. And so we have 2x squared, y, z for this one minus 2x squared y z for this one times I hat minus in brackets 2x y squared z minus 2x y squared z. Okay, then plus in brackets something times k hat. So we have 2x y z squared, and then over here we have minus 2 x, y, z squared. Okay, now each of these differences give 0. So we have 0 I hat plus 0 j hat plus 0 k hat. And of course, this is the 0 vector. Okay, and so I just find this a little bit, well, it just takes longer to calculate this versus the formula that we used earlier. All right. Now, the upside of this is there's not so much to remember, but the downside is it takes a lot to rewrite these things. Okay. And so now let's move on to question 2, since we see we got the same thing in both versions. So in question 2, oh, hang on. No, I haven't calculated div of that function yet. So change this to 1 div. Okay. So calculating div of the vector field f in question 1. Remember, div is the sum of the partial derivatives. So up here, sum. So this is scalar. So we're differentiating with respect to x, y squared, z squared, adding the derivative with respect to y of x squared, y, z squared, and adding to that the derivative with respect to z of x squared, y squared, z. Okay? And so simplifying this, we have y squared, z squared plus x squared, z squared plus x squared, y squared. Okay, so notice that since this is a sum of 3 squares, that this is always greater or equal to 0, and is 0 only where x, y, and z are all 0. All right, so now let's move on to question 2, where we have f equals the vector 0, x cubed, y, z squared, y to the 4th, z cubed. And so our formula says, let's call this A, let's call this one B, let's call this one C. Curl of f is, okay, so here's our formula for curl. So let's sub in C, A, and B. Okay, so having subbed these in, let's take these partial derivatives and then subtract. So 4y cubed, z cubed, 0, 3x squared y, z squared, minus 2x cubed y, z, 0, and 0. Okay, subtracting, we have 4y cubed, z cubed, minus 2x cubed, y, z, and then we have 0, and then we have 3x squared y, z squared. All right, so there's the curl. Okay, so now let's take div of this function right here. So it's the sum of 0 differentiated with respect to x plus x cubed y, z squared differentiated with respect to y plus y to the 4th, z cubed differentiated with respect to z. Okay, so simplifying these and adding that together, we have 0 plus x cubed z squared plus 3y to the 4th z squared. Okay, so these two are not like terms, so we just have x cubed z squared plus 3y to the 4th z squared for div. Okay, so it's occurred to me that this is probably a somewhat better form of the curl formula, where the components of the vector field uppercase f are uppercase x, uppercase y, uppercase z, and then I can use the lowercase letters x, y, and z as they are in the formula. Okay, so for example, let's do question 3 using this formula. So in question 3, we have uppercase F equals x, y, z, 0 minus x squared y. Okay, and so this is our x, uppercase y, uppercase z. This is uppercase x, this is uppercase y, this is uppercase z in this case. And so we're going to use this formula. So the curl of F is, and notice here that we can think of this as a rotation pushing this down by 1, and so then the z comes up to the top, and then if we do that again, push this down 1, then we've got the y at the top, then z, and then x, and then the subscripts match what we have here, so z, x, and y. Okay, so let's sub these in, and now we can simplify this. Okay, now subtracting, we have minus x squared, then we have xy plus 2xy gives us 3xy, and then minus xz. Okay, and so this is the curl of F in question 3. All right, so now let's do div of F. for the vector field in question 3. So div of xyz 0 minus x squared y is the sum of the partial derivatives. So we have yz plus 0 plus 0, which is just yz. All right, so moving on to question 4. Okay, so here we have f, here we have our formula. So then the curl of f is given by the derivative of xyz squared with respect to y, then the derivative of x squared y z with respect to z, and then the derivative of xy squared z with respect to x. Then we subtract the derivative of xy squared z with respect to z, the derivative of xyz squared with respect to x, the derivative of x squared y z with respect to y. Okay, so we calculate each of these partial derivatives and then subtract. So x z squared, x squared y squared z, minus xy squared, yz squared, x squared z. Okay, so subtracting these, we have x z squared minus xy squared, x squared y minus y z squared, y squared z minus x squared z. Okay, so there's our curl vector. Now let's calculate div of this vector field. So we have the sum of the 3 partial derivatives. Okay, so next, differentiating each of these, we have 2xyz plus 2xyz plus 2xyz. Okay, I can see that there are 2 plus 2 plus 2 is 6. So 6xyz is div. Okay, question 5. So this says, for exercises 5 and 6 below, refer to the figure. So what we're looking at are these 3 vector fields here. So the question asks, what is the sign of div of that vector field f? And so when the arrows lined up head to tail are getting smaller in magnitude as you go along, then in that case, like what you see up here at the top left, we have div f negative. Okay, so I'll give you an example here. For example, if the vector field f is 0, 1 on y, 0, then div of f would be the derivative of 0 with respect to x plus the derivative of 1 on y with respect to y partially plus the derivative of 0 with respect to z partially. Okay, now if you differentiate 1 on y, or y to the minus 1 with respect to y, the minus 1 comes down, so you have minus y to the minus 2, or minus 1 on y squared for this example. And so if you plot this, I'll open up Mathematica to show you. So running stream plot here, this is an example. You can barely see that the arrows are getting smaller as you go along with this example, but it looks a lot like what we have there in the PDF, like this one. And so this is negative for all y not equal to 0. Okay, so arrows getting smaller. I'm going to say reducing in magnitude when head to tail, like what you see there in the top left. So in the top left, we have an example of div f negative. All right, so let's have a look at the vector field to the right of that. There we have an example where div f is positive. The arrows stacked head to tail are increasing in magnitude as you go along. So let me find an example of that for you. So if f were the vector field x, y, 0, then div f would be the sum of the partial derivatives. So 1 plus 1 plus 0, in this case it would be 2, that's positive. And if we plot that using Mathematica, this is what we get. So here you see the arrows increasing in magnitude as you go along. So arrows increasing in magnitude when they're head to tail. Okay, so now let's look at our third diagram. So in the third diagram, we have arrows seeming to have the same magnitude when they're lined up head to tail. And so in that case, we have div f equal to 0. So for example, if we had f equal to y minus 2, 0, and 0, then it might look like what we have there in this diagram on the bottom left. So let's calculate div in this case. So differentiating y minus 2 with respect to x partially gives 0. differentiating 0 with respect to y partially gives 0, and differentiating 0 with respect to z partially gives 0. The sum of those is 0. Okay, now there's a word for this. It's incompressible. Okay, so now let's look at question 6. What is the curl of each of these vector fields? Are these vector fields irrotational or are they rotational? So in this question 6, what you're asking here is, would a beach ball in a river with this kind of current, would it have a tendency to spin? So for the bottom left, yes, this would have a tendency to spin clockwise, but for the top left, there would be no tendency to spin, and for the top right, there would be no tendency to spin. So if we look at each of these examples, this vector field, and this vector field, we can calculate the curl for each of those. So for this one, so curl of f is 0, the 0 vector for the top left, so irrotational. Okay, now for this vector field in the top right, we also have curl f is the 0 vector. So this vector field on the top right is also irrotational. Okay, now, however, for this vector field in the bottom left, and I'm using this example, we can calculate curl of this vector. And so what we get is curl of f is minus k hat, which we can write as 0, 0, minus 1. Okay, now, according to the right-hand rule, to determine whether the curl vector points into the page or out of the page, just curl your hand around and think about where the thumb points. All right, so here, if we take our hand and point it down, we can see that the beach ball will tend to go clockwise. And where does the thumb go? It points down. So that's the direction of the curl vector. So you can just take your thumb on your right hand, and with your left hand, if you can, maybe just write the word curl, right? But obviously don't do that in your exam. Okay, question 8. Determine for this vector field f equal to y squared z cubed, 2xy z cubed, 3xy squared z squared, whether or not the vector field is conservative. If so, find lowercase f such that the vector field f is grad of lowercase f. Now, let's go ahead and look at what the definition of conservative was. So I'll scroll up. If the work done in moving an object from the point A to the point B is independent of the path taken, then we say f is conservative. If f is a vector field that is the gradient of some function lowercase f, in other words, given the vector field f, there exists a scalar function f of x, y, and z such that the vector field f is grad of the scalar function f, then f is conservative. Down here, there's a theorem that says if f is defined on 3 space, has continuous partial derivatives, and the curl of the vector field f is the 0 vector, then f is conservative. The converse is true defined on some domain U, but there's probably more to that convert. Okay, so what we need to do here is calculate the curl of this vector field f. If we get 0, then f is conservative, and hence we can find a lowercase f or a scalar function lowercase f such that the vector field f is grad of the scalar field f. Okay, so calculating curl of f, calling this up here x, uppercase y, and uppercase z. So curl of f is given by z subscript y, x subscript z, y subscript x, minus uppercase y subscript z, uppercase z subscript x, uppercase x subscript y. Okay, so I've copied those out. So now I need to differentiate these. So we're differentiating this function with respect to y. So the derivative of y squared with respect to y is 2y. 3 times 2 is 6. So 6xy z squared. Down here we have 3y squared z squared. Here we have 2y z cubed. Okay, differentiating this function with respect to z partially gives 6xy z squared. Then we have 3y squared z squared. Then we have 2y z cubed. Okay, now each of these are the same. So subtracting gives the 0 vector. And so we learn then that curl f is the 0 vector. So the vector field f is irrotational, and hence vector field f is conservative. So there exists a potential function, lowercase f, satisfying vector field f is grad of lowercase l. And so our next task would be to find it. So to find lowercase f, we would set out uppercase f, y squared z cubed, 2xy z cubed, 3x y squared z squared equals f subscript x, f subscript y, f subscript z. So we have one vector equation that gives rise to three scalar equations. But what I want to do at this point is point out, we go back up to this little diagram here at the bottom left, a beach ball here in this particular vector field, which is not this one, by the way, but the bottom left diagram, that particular vector field, a beach ball would have a tendency to spin in such a river. So that would be rotational. And so if we were moving a beach ball from, say, down the bottom where my cursor is to over here where the cursor is now, it wouldn't matter which path we took as to how much work would be required in pushing that beach ball. So if we took this route, it would be different than if we went over here. So a feature of a conservative vector field is that the work done in moving a point from A to B is path independent. So in this case, for this particular vector field, the work done in moving a particle from point A to point B will be path independent because our vector field here is conservative because it's irrotational. Simultaneous scalar equations. And so now let's label these equation 1, equation 2, and equation 3. So what we need to do is take equation 1 and integrate with respect to x. So f is the integral of y squared z cubed with respect to x. Now this is a partial differential equation, so we need to treat this as a partial integral. We write it with an ordinary d though. So this integral, we're treating this here as a constant, so we have x y squared z cubed plus some function g of the other two letters y and z. Because if we were to differentiate this line partially with respect to x, this here being a function of only y and z, the derivative of this g with respect to x partially would be 0, and the derivative of x y squared z cubed would be y squared z cubed. And so the derivative of this partially with respect to x would be this. Okay, so going the other way, this is our integral. Okay, so now taking this, let's call it equation 4, and differentiating with respect to, and I've abbreviated this, y, and the reason why we want to do this is so that we can match that with equation 2. Okay, so we have f y equals, differentiating this with respect to y partially gives 2xy z cubed, and the derivative of g with respect to y partially, let's just write it as g subscript y, y comma z. Okay, and so this is equal to, by equation 2, 2xy z cubed by equation 2. Now we can see that these two match. Okay, and so what this tells us, so we've got 2xy z cubed is equal to 2xy z cubed plus g subscript y of y and z. So what this tells us then, we see that g subscript y of y and z has to be 0. And so now integrating this with respect to y, we have g, a function of y and z, is the integral of 0 with respect to y. And so since this is a function of y and z, the other letter here when we integrate is z. So we have just a function h, let's say, of z. Okay, so what we've learned then is f, a function of x, y, and z, is xy squared z cubed plus some function h of z. So we're getting somewhere here because we've learned that that is only a function of z, not of x and y. All right, so now differentiating this with respect to z so that we can compare that with equation 3 up here, we have f subscript z equals 3x y squared z squared plus h subscript z of z. And so matching that with equation 3, this is equal to 3x y squared z squared. And so now we see, because this is equal to this, these two being equal, so we have to have a h subscript z of z equals 0. And so then integrating gives h equal to just a constant. All right, and so then what we've learned is that f of x, y, and z is equal to xy squared z cubed plus a constant, and this satisfies uppercase F equal to grad of lowercase f. So we found our potential function. Okay, question 9. So we have a vector field, and so let's label the components uppercase X, Y, and uppercase Z so that we can use our formula. We want to calculate curl of this vector field so that we can determine whether or not f is conservative. So if we get curl f is 0, then it's conservative, and hence we can find a potential function lowercase f. So curl of f. Okay, so simplifying this, subtracting. All right, so now we need to simplify each of these partial derivatives and take that difference. So we get 4x squared z cubed, then we have 4xy z cubed, then we have 2x z to the fourth minus 4x squared z cubed, then we have 4 times 2 is 8, x y z cubed, and then we have x z to the fourth. Okay, so these two vanish. These two do not vanish. We have minus 4xy z cubed. These are like terms, and their difference is x z to the fourth there. All right, so this is not the zero vector in general. And so we see then that the vector field f is not conservative. And so there is no scalar field lowercase f such that uppercase f is grad of lowercase f. So there is no scalar f. Okay, question 10. So let's let this be uppercase x, uppercase y, uppercase z, as we've been doing. Okay, and calculate curl of f. So we have z subscript y, x subscript z, y subscript x, minus y subscript z, z subscript x, x subscript y. So subbing these things in. Okay, so now we need to take each of these partial derivatives and then subtract. So the derivative of cos is minus sine, so we have minus x sine of y. Then the derivative of z with respect to z is 1, so then we have cos of y. The derivative of x with respect to x is 1, so we have z sine of y. Okay, next differentiating z with respect to z gives x sine y. Differentiating x with respect to x gives 1, so cos of y. And then differentiating cos with respect to y gives minus sine, so minus z sine of y. Okay, so now when we subtract, we can see that not quite everything vanishes. So we get minus 2x sine of y, 0, and then 2z sine of y. Okay, so in general, this is not equal to the zero vector, so f is not conservative. All right, now we can change f somewhat so that we do get a conservative vector field. So why don't we do that here as an extra problem? So let's call this problem 10.5. Okay, so in 10.5, let's suppose that we instead have z cos of y minus x z sine of y and x cos of y. So I believe this one is conservative. Let's just check by calculating the curl of f. Okay, so I've substituted these in here, and so now let's differentiate this. X cos y differentiates with respect to y to give minus x sine of y. Z cos y differentiates to give cos of y. Minus x z sine y with respect to x partially gives minus z sine of y. Okay, next, differentiating minus x z sine y with respect to z partially gives minus x sine of y. Differentiating this with respect to x partially gives cos of y. And differentiating z cos of y with respect to y partially gives minus z sine of y. Okay, now this vector is the same as this vector, so the difference here is the zero vector. So we see then that curl f is the zero vector, so the vector field f is conservative, and so f such that uppercase f is grad lowercase f exists, and we can find it. Okay, and so then to find it, well, we'll write f, which is z cos y minus x z sine y x cos y equal to the vector containing f subscript x, f subscript y, f subscript z. So this is a single scalar equation that gives rise to 3 vector equations. And so now we can write those 3 vector equations and solve them as a simultaneous system. And so let's also label these 1, 2, and 3, as in equation 1, equation 2, equation 3. Okay, so now to solve this system, we'll take equation 1 and integrate both sides with respect to x. And so we'll get f is a function of x, y, and z. It's equal to the integral of z cos of y with respect to x. This is to be understood as taking that integral partially, because this was a partial differential equation. Okay, so integrating z cos y. Now z and cos y, they don't have x in them, so we can treat those two as constants. And so this integral here is x z cos of y. And then we need a plus c in our integral, but since this is a partial integral, the analog of c is a function. So let's call that g. It's a function of the other 2 letters, y and z. So we don't quite know the nature of the function yet, other than it doesn't have an x in it. All right, so now this is our f. We want to differentiate this with respect to y partially so that we can compare it with equation 2, because equation 2 has an f subscript y. So we'll say differentiating with respect to y, we have f subscript y equals minus x z sine of y plus g subscript y of y and z. Okay, now so by equation 2, we get minus x z sine of y. So in equation 2, this is our fy, but this is our fy as well that we got from differentiating this line. So this is equal to minus x z sine y plus g subscript y of y and z. Now the two of these are the same, and so what we learn here is that g subscript y is 0. And what we get here when we integrate this with respect to y, we get g is the integral of 0 with respect to y, and so the other letter here is z, so we just have another function, say h of z. And so what this says then is that up here we can replace this g of y with h of z. Okay, so now differentiating this with respect to z partially, we have f subscript z equals x cos of y plus h subscript z of z. And by equation 3 here, f subscript z is x cos of y, and so matching equations gives us that this is x cos of y plus h of z, or h subscript z of z. And so since these two match, we see h subscript z of z is 0, and so integrating that with respect to z partially gives h of z has to be just a constant, which then tells us what lowercase f is. Okay, so our conclusion here is that this function is x z cos of y plus a constant, and it satisfies the vector field f is grad of lowercase f. Okay, question 11, we have f is xy z squared x squared y z squared x squared y squared z. And so taking the curl of this, okay, so here's our formula, simplifying this by subbing in. Okay, so now taking these partial derivatives, we have 2x squared z, 2xy z, 2xy z squared. Then over here we have 2x squared y z. Then we have 2xy squared z, and we have x z squared. Okay, so we can see that the difference here does not give 0. So here's our curl vector. This is not the 0 vector, and so f cannot be conservative. Okay, question 12. Show that any vector field of the form f equal to f of x, g of y, and h of z is irrotational. So what we need to do here is calculate the curl of f and show that the curl of f is 0. But let's label this x, y, z so we can use our little formula here. Okay, so having subbed these in, we need to differentiate these. So this says differentiate the function of z, h, with respect to y partially, and of course we get 0 for that because there are no y's in that. Similarly, for this we get 0, and for this we get 0, for this we get 0, for this we get 0, for this we get 0. Okay, so the difference of these two vectors is the 0 vector, and so F is irrotational. F's irrotational. Okay, question 13. So here we have F is the vector field consisting of a function lowercase f of y and z, a function lowercase g of x and z, and a function lowercase h of x and y. Let's label these uppercase x, uppercase y, and uppercase z. Okay, now calculating div, we're asked to show that this vector field is incompressible, so div of the vector field f is x subscript x plus y subscript y plus z subscript z. And so we're differentiating with respect to x, f of y and z, adding to that the derivative with respect to y of g of x and z plus the derivative with respect to z of h of x and y. Okay, so there's no x in this function, so this derivative is 0. There's no y in this, so this derivative is 0. And there's no z in this, so this derivative is 0. 0 plus 0 plus 0 is 0. So we see because div f is 0, f is incompressible. Okay, so in questions 14 through 18, we're asked to verify some identities. So let's begin with 14. So div of vector field f1 plus vector field f2, we're asked to verify that this is the sum of the divs. Okay, so let's begin with, say, the left-hand side. So we'll say let f1 be equal to x1, y1, z1, and f2 be equal to x2, y2, z2. So div of the sum of f1 and f2 is div of x1 plus x2, y1 plus y2, z1 plus z2. So our assumption here is that these are functions of x, y, and z, lowercase x, lowercase y, lowercase z. Okay, and so this is the derivative with respect to x of x1 plus x2, and then plus the derivative with respect to y of uppercase y1 plus uppercase y2 plus the derivative with respect to z of uppercase z1 plus uppercase z2. And so remember where you're going with this. You want to show that this is div of f1 plus div of f2. So it seems we need to break these up. So this is the derivative with respect to x of x1 plus the derivative with respect to y of y1 plus the derivative with respect to z of z1 plus the derivative with respect to x of x2 plus the derivative with respect to y of y2 plus the derivative with respect to z of z2. And so this sum is div of f1. This sum is div of f2. So we have div of f1 plus div of f2, and the verification is complete. Okay, question 15. We're asked to verify that curl of f1 plus f2 is the sum of the curls. Okay, so again, let's let f1 be equal to x1, y1, z1. Here, these are functions of lowercase x, lowercase y, and lowercase z. Let's let f2 be x2, y2, z2. And so f1 plus f2 is x1 plus x2, y1 plus y2, z1 plus z2. And so then curl of that is the curl of this. And so according to our formula, we take the z component, differentiate that with respect to y. We take the x component, differentiate that with respect to z. Then we take the y component, differentiate that with respect to x, subtract. Now we take the y component and differentiate that with respect to z. We take the z component, differentiate that with respect to x. And finally, we take the x component and differentiate that with respect to y. Okay, and so now we can express this as z1 subscript y plus z2 subscript y minus y1 subscript z minus y2 subscript z in the top row, x1 subscript z, x2 subscript z minus z1 subscript x minus z2 subscript x. Then in the third row, y1 subscript x plus y2 subscript x minus x1 subscript y minus x2 subscript y. Okay, so let's bring this over next to this over next to this over next to this, because we want to show that that part of it is curl F1. Okay, so here's our top row separated, second row separated, and the third row separated, just like that. Okay, so now that we have this here is clearly curl of F1, this here is clearly curl of F2, and so we see then that curl of the sum of F1 and F2 is curl of F1 plus curl of F2. Okay, question 16. In this one, we're asked to show that div of scalar function f times vector field uppercase F is equal to f div of uppercase F plus uppercase F dot grad of lowercase f. All right, and so let's let uppercase F be uppercase X, uppercase Y, uppercase Z. So dealing with the left-hand side, div of scalar function f times a vector field uppercase F, we have div of, taking the scalar product here, we have div of lowercase f, uppercase X, lowercase f, uppercase Y, lowercase f, uppercase Z, and so this is the partial derivative with respect to x of f times x plus the partial derivative with respect to y of f times y plus the partial derivative with respect to z of f times z. Okay, so these are uppercase, these down here are lowercase, uppercase, lowercase, uppercase, lowercase. All right, now because presumably lowercase f and uppercase x are functions of lowercase x, lowercase y, and lowercase z, we need to use the product rule on them. And so using the product rule, we pull one out, differentiate the other one. I'm changing notations here, and then swap the role of these. So f subscript x times uppercase x, same with this, okay, and the same with this one. Okay, now let's see, where are we going here? We want to express this as f div f plus f dot grad of lowercase f. So we can see that already, but let's separate this, pulling out the single f's times something together. So let's call this f uppercase x subscript lowercase x plus f uppercase y subscript lowercase y plus f uppercase z subscript lowercase z. So this here is our lowercase f div uppercase f, and then what remains there is fx plus fy y plus fz z, and this here is a dot product or a scalar product. It's a scalar product of these two. All right, so this first one is f times div x, y, z, and then this one here we can express as a dot product x, y, z dot fx, fy, fz, and then now it's pretty obvious that this is the same as what we have up here, okay, and we have verified that identity there. Okay, moving on to question 17. So let's let f1 be equal to x1, y1, z1 again, and f2 equal to x2, y2, z2. Okay, so we need to take the cross product of the two of these vector fields, and so let's use the formula given by this pretend determinant I, j, k, x1, y1, z1, x2, y2, z2. Okay, expanding this determinant, we have this. Okay, and now simplifying, we have y1, z2 minus y2, z1 brackets I hat minus x1, z2 minus x2, z1 j hat plus x1, z2 minus x2, z1. Oh, I feel like I got something a bit off here. These should have been y1. Yeah, these are y1 and y2 in the k hat position. Okay, so that changes this. All right, there we go, times k hat. Now we can express this vertically in rows, just like this. Okay, and so this is f1 cross f2. And so now we want to take div of this. So we have the derivative with respect to x of y1 z2 minus y2 z2. That should be z1, shouldn't it? Yes, z1 plus the derivative with respect to y of x2 z1 minus x1 z2 plus the derivative with respect to z of x1 y2 minus x2 y1. All right. And so simplifying this, we're going to need the product rule here. Using the product rule on this one, we have y1 subscript x times z2 plus z2 times, z2 subscript x times y1, and then minus y2 subscript x z1 minus z1 subscript x y2 plus. Okay, so we have this now, but it looks like a bit of a mess. So what I would suggest that we do then is compare, as in see where we're going. We're attempting to get this right-hand side from this. So we've got to recognize this as this, but it's not so clear from looking at it. So what I would suggest to do is just put a full stop here and start working on the right-hand side. So f2 dot curl of f1 minus f1 dot curl of f2 is x2 y2 z2 dot in brackets, so z1 subscript y minus y1 subscript z. Then we have x1 subscript z minus z1 subscript x. Then we have y1 subscript x minus x1 subscript y for this part of it, and then minus x1 y1 z1 dot z2 subscript y minus y2 subscript z, x2 subscript z minus z2 subscript x, y2 subscript x minus x2 subscript y. Okay, now if we dot this out, I expect we will get what we see above. So let's do at least some of this. So x2 brackets z1 y minus y1 z plus. Okay, so this is this expanded, this dot product expanded, and then we have minus x1 brackets z2 y minus y2 z. Okay, which is this. And so let's have a look. When we expand this, do we have an x2 z1 subscript y over here? Let's have a look. Yes, it's right here. And so a further expansion of this, you can verify yourself that it will give this. Okay, so let's just put, yes, this is equal to the left-hand side, which is div of f1 cross f2. All right, well, that one was a bit of an involved problem. 18. So we're asked to prove that div of grad f cross grad g is 0. Okay, so let's deal with the left-hand side. Div of grad f cross grad g is div of the vector, where we represent this as a determinant. We put in fx, fy, fz, then gx, gy, gz. Okay, so we've got to take div of this vector, but to do that, we first want to calculate the vector itself. So we have div of this. Okay, so simplifying this, we have div of fy gz minus fz gy I hat minus fx gz minus fz gx j hat plus fx gy minus gx fy k hat. Okay, so we can put this in columns if we like, and I'll do that for you. Okay, so there we have it represented with a column. And so to take div of this, of fy gz minus fz gy, we need to differentiate this partially with respect to x, add to that the other partial derivatives. Okay, so here we have this expressed as a sum of 3 partial derivatives, but we need to simplify these derivatives using the product rule. So we have fyx gz plus gzx fy minus fzx gy minus gyx fz. Okay, so we expand those derivatives using the product rule, and this is what we get. Now, search through this and find where you have gz and gz, these two. So this would be the same if only fyx were equal to fxy. All right, but if we look at the question here, Well, it doesn't say so, but I assume that we can assume that that Clairaut's theorem applies here. And so let's just say this is equal to 0 by Clairaut's theorem. And so f(yx) being the same as f(xy), etc. Okay, question 19. So this is an application of Green's theorem, which says, let C be a positively oriented. This is a curve or a path that goes counterclockwise. We're talking about a closed curve here. So let C be a positively oriented, piecewise smooth, so no sharp points, simple closed curve in the plane, and let D be a region bounded by C if P and Q have continuous partial derivatives on an open region that contains D. Then this closed integral can be expressed as a double integral over the region D, where inside we're integrating the two partial derivatives subtracted with respect to A. So let's see an example of this in question 19. So we're asked to evaluate the integral of x to the fourth dx plus xy dy, where C is a triangular curve. And let's just sketch this while we read it. Here are my axes. And so we start the curve at the point 0, 0, then we go to 1, 0, and then we go to 0, 1 this way, and then we go back to 0, 0. Okay, so this is the curve C. Inside here is the region D. Now this diagonal line here is the line y equals minus x plus 1, an intercept at 1. And so now we can express the region D as the set of all points x, y, such that x is between 0 and 1, and y greater or equal to 0, but it's less than or equal to 1 minus x, because it's below this line. So if you just pick a point here at the tip of my pen and think about the point with the same x value above it on the line, the y value here is 1 minus x, and that's above this, so it's greater than the y value here. So that's that inequality. Okay, and I need to end that curly bracket there. Okay, so we've described the set of points inside this. Okay, so according to Green's theorem, because we have a positively oriented, so counterclockwise arrows, piecewise smooth, simple connected curve in the plane, D is bounded by C. Now P is this and Q is this. So let P be equal to x to the fourth and Q be equal to x times y. These two functions do have continuous partial derivatives on D, and so let's differentiate these. The derivative of Q partially with respect to x is y, and the derivative of P with respect to y is 0. And so the theorem says that the integral x to the fourth dx plus xy dy is equal to the double integral over D of Q subscript x, which is y, minus P subscript y, which is 0, dA. Okay, and so now let's simplify this double integral. So looking at our region D there, so let's put the dy first and then the dx. So according to what the y are doing, the y are going from 0 to 1 minus x, and then the x are going from 0 to 1. Okay, and so now we can simply integrate this. So integral from 0 to 1, let's integrate that y with respect to y. So we have 1/2 y squared, and I'll put in y equals 0 to y equals 1 minus x. And then the result we will integrate with respect to x. Okay, so subbing those two things in, we have this. And so now we can integrate 1/2 1 minus x to the power of 2 with respect to x. And we get minus 1/6 1 minus x to the power of 3 between 0 and 1. And then when we sub in 1, this vanishes. When we sub in 0, we have minus 1/6, which is 1/6. Okay, question 20 is an application of Stokes' theorem. Let S be an oriented piecewise smooth surface that is bounded by a simple closed piecewise smooth boundary curve C with positive orientation. Let F be a vector field whose components have continuous partial derivatives on an open region in 3 space that contains S. Then the integral of F dot dr can be expressed as a double integral over S of curl F dot ds. And so I present this here a little bit prematurely as an application of the curl vector because we've been studying the curl vector here. Okay, so let's get started with question 20. We have the vector field F. Write this as a column, minus y squared x z squared. And C is the intersection of the plane and the cylinder. So I'll write the cylinder first, x squared plus y squared equals 1. And the plane, y plus z equals 2. Okay, so while we're at it, let's draw a little picture of this by hand. So we have a plane, something like this. And then we have the cylinder that intersects with this along a boundary like that, coming up like this. Okay, and so we are asked to evaluate the integral over C. So this here is C, this dotted line of f dot dr. Okay, and so we'll use Stokes' theorem to do this. So first, according to Stokes' theorem, we need to calculate the curl of f. So let's do that down here on the side. And so this is z squared differentiated with respect to y partially. Then we have minus y squared differentiated with respect to z partially. And we have x differentiated with respect to x partially. And we subtract the derivative of x with respect to z partially, then z squared differentiated with respect to x partially, and minus y squared differentiated with respect to y partially. Okay, so simplifying this, we have 0 for this, 0 for this, 1 for this, minus 0 for this, 0 for this, and minus 2y for the last one. Okay, and so our curl vector is the vector 0, 0, 1 plus 2y. So this is curl of f. Okay, now according to Stokes' theorem, we can write this as the double integral over s of curl of f dot ds. And so taking that dot product, we can express this as the double integral of 1 plus 2y dA over region D. And so at this point, we want to change to polar coordinates. And so we have integral from 0 to 2 pi, integral from 0 to 1, 1 plus 2r sine theta for y. And then we replace dA with r dr d theta. Okay, and so now it just comes down to an ordinary calculation. So expanding the r in, we have this. Now integrating this function with respect to r partially, we have a half r squared plus 2/3 r cubed sine theta 0 to 1 and then d theta. Okay, so subbing in, replacing r with 1 and then r with 0 and subtracting, we have this. Okay, so now integrating this with respect to theta, half theta, the integral of sine of theta with respect to theta is minus cos of theta. And so now we sub in 2 pi, and 1/2 of 2 pi is just pi. So we get cos of 2 pi being 1, so minus 2/3. And then we subtract 1/2 of 0 minus 2/3 cos 0. Cos 0 is 1, so minus 2/3. Now these 2/3 will vanish because this is a plus 2/3, this is a minus 2/3, and this is a 0. So we just get pi out of this, and we're done.